Vision transformers have completely reshaped computer vision. But there's a quiet, structural flaw in how they actually see. When a VT looks at an image, it doesn't always focus on the object. It focuses on the background. It latches onto spurious correlations, watermarks, or textures, and confidently calls it a day. This isn't just an interpretability issue. It's a fundamental robustness problem that limits out-of-distribution generalization and encourages shortcut learning. Today, we're breaking down a new paper that fixes this by doing something counterintuitive, teaching the transformer to actively ignore things. We're talking about inhibited self-attention, a mechanism that brings biological push-pull inhibition into deep learning, sharpens object focus, and dramatically improves model reliability. To understand why this works, we first need to look at how standard self-attention actually computes relationships between image patches. In a vision transformer, every image patch gets mapped to query, key, and value vectors. The raw attention scores are just dot products between queries and keys, scaled by the square root of the key dimension. These raw scores can be positive or negative. A high positive score means strong similarity or relevance. A negative score means strong dissimilarity or conflict. But here's the catch. Standard self-attention immediately passes these scores through a softmax function. Softmax exponentiates every value, which means it turns those crucial negative scores into tiny positive probabilities. It effectively throws away the inhibitory signal. The model loses the ability to actively suppress irrelevant or conflicting patches. It can only amplify what it likes, not actively ignore what it doesn't. This is where the authors drew inspiration from neuroscience. In the primary visual cortex, neurons don't just excite each other. They use push-pull inhibition and lateral inhibition to sharpen edges and suppress background noise. The proposed inhibited self-attention, or ISA, brings this exact principle into the transformer architecture. Instead of discarding negative scores, ISA calculates two distributions: a standard softmax distribution for positive attention and a softmin distribution for negative attention. Softmin is just softmax applied to the negated raw scores, so it assigns higher weights to patches with the lowest similarity scores. Then it combines them using a competitive inhibition formula. You take the positive attention map, subtract a scaled version of the negative attention map, clamp the result to a small epsilon to prevent vanishing gradients, and finally L1 normalize the row. The hyperparameter alpha controls how aggressively the model suppresses irrelevant features. And the best part? This is a drop-in replacement. Zero extra parameters, zero extra floating point operations. You just swap out the attention block, and the math handles the rest. But how do you actually prove the model is looking at the right thing? The authors introduce a new metric called attention on objects, or AO. Instead of just checking where the single highest attention peak is, AO uses pixel-level segmentation masks to calculate the ratio of attention mass landing directly on the object versus the background. They also introduce a thresholded version of this metric, where they progressively filter out low-confidence attention tokens. What they found is striking. At high thresholds, where only the most confident attention tokens remain, ISA consistently keeps significantly more attention mass on the actual object. The standard VT tends to spread its attention thinly across the scene or fixate on background shortcuts, while ISA's raw score distribution is naturally regularized. It avoids that winner-takes-all fixation on noise and concentrates attention on discriminative object parts. So does this sharper focus actually translate to better performance? The experiments are extensive. On clean ImageNet-1K, ISA maintains competitive accuracy. But the real gains show up when you stress-test the models. On ImageNet-Watermark, where Chinese characters are artificially pasted onto images to create spurious correlations, standard VTs crash in accuracy and heavily rely on the watermark. ISA significantly reduces that shortcut reliance. On the Waterbirds dataset, where birds are artificially placed on mismatched backgrounds during training, ISA improves worst group accuracy by over 2 percentage points, proving it's actually learning the bird, not the pond or the grass. For out-of-distribution generalization on ImageNet renditions, and robustness to heavy corruptions on ImageNet-C, models with ISA consistently outperform baselines. The inhibition mechanism forces the model to build more causal, object-centric representations, rather than leaning on coincidental contextual cues. They didn't stop at classification. They extended ISA to object detection using a DINO-style architecture with deformable attention. They introduced attention on detected objects, a metric that measures how precisely the decoder's sampling points focus inside the ground truth bounding box. ISA DINO not only improves mean average precision, but also samples attention more tightly around the actual object. They even created a custom background dataset, Coco Background, where objects are placed against unnatural scenes like volcanoes or glaciers. While standard detectors suffer massive performance drops when the context changes, ISA DINO maintains its accuracy. The model isn't cheating by recognizing the scene. It's actually finding the object. What's really exciting about inhibited self-attention is how elegantly it solves a core architectural blind spot. By reclaiming the negative attention scores that softmax routinely discards, ISA gives transformers the ability to actively suppress noise, sharpen feature selectivity, and ground their predictions in actual object structure rather than background correlation. It's a drop-in, zero-overhead modification that makes vision models more robust, more interpretable, and fundamentally more reliable. As we push foundation models into real-world applications, mechanisms like this will be critical for moving past shortcut learning and toward truly generalizable computer vision. If you want to dive into the math, see the attention visualizations, or check out the code, I've linked the paper and repository in the description. Thanks for watching, and I'll see you in the next one.